right. So in my lectures, I'm going to continue talking about the rank 1 abelian Stark conjecture that Samit introduced yesterday. But I'm going to have a slightly different focus. Samit talked up the analogy, which is extremely useful, between the Stark conjecture and the Birch-Swinnerton-Dyer conjecture, and how they can be commonly refined by equivariant Tamagawa number conjectures. And it's certainly true that one can use sophisticated techniques from algebraic geometry and automorphic forms to analyze both of these conjectures, BSD and Stark. But I'm going to back away a bit from the analogy and talk about a different set of techniques for attacking Stark's conjecture, or at least refining Stark's conjecture and constructing explicitly units in number fields that's not based on algebraic geometry at all and won't mention automorphic forms at all, but instead is based on Euclidean convex geometry, really with a field. It has a bit of a field-like geometry of numbers. And this is a method introduced by Shintani in the mid-70s to analyze zeta functions and prove the rationality of their values at negative integers. So I'm going to be taking a look at these techniques developed by Shintani and their applications to the rank 1 abelian Stark conjecture. But before I do that, I'd like to make a little addendum to what we talked about, what Samit talked about last time. People have been asking exactly what's known about the rank 1 abelian Stark conjecture in these three cases we've subdivided things into. So let me first talk about the cases known about the rank 1 abelian Stark conjecture. So recall we divided everything up into three cases: TR infinity, ATR, and TRP. So the way to parse this is the letters tell you what the signature of the base field is, and the subscript tells you what the what kind of distinguished prime we're looking at. And in the ATR case, well, every complex place automatically splits completely, so we don't need a subscript there. So what's known in these three cases is, for the case f equals q, in TR infinity, this is really the example, the cyclotomic example that Samit worked out for us. And in the ATR case, what's known is, well, only the most basic, almost totally real field, the case where f is imaginary quadratic. And this is, you construct Stark units. Well, in this case, the Stark units are exactly the elliptic units, which are constructed using CM theory. And that's the only case where CM theory helps you construct units, even though a CM theory is applicable for every CM field. Units don't seem to come out naturally from it, except for the case where you have a base field, where your base field is Q and your CM field is F. And in the case TRP, well, the case F equals Q is really Stickelberger's theorem. And Gross also proved a refinement of it. And Gross's refinement for other totally real base fields is this was dealt with under a few hypotheses by what's the alphabetical order? Delmont, Dasgupta, and Pollack. And this was a year or two ago. But I want to emphasize that the only ground fields F, such that Stark is known, or rank 1 abelian Stark, I should say, is known for every extension K over F, is F equals Q, or F equals imaginary quadratic. All right, so the case is the cyclotomic case and the case where you have modular units available are really the only cases where our knowledge can be really said to be completely satisfactory. And so this is the current state of the art. And what I'll continue talking about now are, yes, sorry. In function fields, I think much more is known. You can use the theory of rank 1 Drinfeld modules to I think, essentially prove rank 1 abelian star conjecture. I think it's due to Hayes. Is that correct? Okay, Deline and Hayes. Okay, so I'd like to begin with a bit of motivation. And I'd like to take this motivation from the simplest ATR case, namely the case where f is imaginary quadratic. And we'll put ourselves in our usual situation where k over f is an abelian extension. And we have this set of places that we introduced last time, and I'll take it to be the minimal set possible, namely the infinite place of f together with the places of f ramified in K. Okay, and so I'll take V to be the infinite place of f. This is part of our data with which we state the Stark conjecture. And we'll look at a place W of K which divides V. And Stark's conjecture says that, in this case, that zeta prime K over F, relative to this set of places F, if we look at the partial zeta function associated to an element sigma in the Galois group of K over F, and we evaluate this derivative at 0, what we get is 1 over E times the log of the absolute value of a Stark unit, or the image of a Stark unit under this automorphism sigma, and we take the absolute value with respect to this W. All right, so as was pointed out last time, U is a complex number, and the absolute value only tells you, well, it's what circle it lies on in the complex plane, and to really determine this unit entirely, we need to know something about its argument. So we'd like a refined version of at least this conjecture that allows us to actually produce an explicit candidate for the unit. Of course, this is one of the cases where we can do it using other means, but it's helpful to start by thinking about this case. And what we really have to do is, the problem is the place W, it mashes together the two embeddings which comprise it, the two complex conjugate embeddings. And we need to separate those out in order to get the unit itself as opposed to just its absolute value. So if we think about V being, the place V being composed of the two embeddings, V1 and V2, of F into C, and look at the two places comprising W, which extend V1 and V2 respectively, from K into C, so W1 bar is W2, and V1 bar is V2, then we can rewrite this expression, or we can rewrite Stark's conjecture in the form zeta prime K over F S sigma 0 is 1 over E times the logarithm of W1 of U sigma plus W2 of U sigma. Sorry, and I should have a log here. So what we really have to do is find a way to separate out the two embeddings that comprise this place W in order to allow ourselves to access this information about the logarithms of these two embedded images separately. And that's what Shintani's method allows us to do. It involves looking at all the embeddings and not all the places. So that's the extra data we carry along in order to refine this conjecture. Now I should say, of course, that CM theory, in this case of imaginary quadratic fields, says that well, Wi of u sigma is just a Cm value of an elliptic unit. And in fact, we can, in the case where everything is known in this imaginary quadratic case, Shintani actually reproved the Kronecker limit formula, which essentially is the statement, is the precise statement of this, using, well, his method. So, and I'll make some remarks a little later on about how Shintani zeta functions and the elliptic functions from which Siegel units are constructed are related. So there is an explicit bridge in this CM case between the classical CM theory and Shintani's method. And Shintani's method, though, it seems to have more potential. Shintani's method, though, seems to have more potential for generalization, or it seems more evident how to approach generalization than the CM-based methods. Yeah. Okay, so the idea, again, is to separate out the two embeddings corresponding to a place, a complex place. So on the level of the zeta functions, I'd like to, Shintani allows us to express this zeta function where k over f is still an extension of an imaginary quadratic field as before, as a sum of two zeta functions, say z1 of s plus z2 of s. So this is the case where f over q is 2. And of course, there are choices involved here, so the zi of s are not well defined. There are choices involved, but zi prime of 0 is mostly well defined. In the sense that it's well defined up to, well, however much we can expect a perspective logarithm to be well defined, namely up to an integral multiple of 2 pi I. But there's also this business with a root of unity that always fudges up these star computations, so there'll be some kind of denominator which can be explicitly bounded involved, which may be able to be removed by smoothing methods, introducing this set T of the second set T of places, the way we saw yesterday. And the first place where such a decomposition arises is in Shintani's proof. Of the rationality of zeta values of totally real fields. And this appeared in 1976. All right, so although it was introduced in this context of proving certain rationality results, his methods have had further applications, some of which I'll describe. But first, I'd like to just discuss or introduce Shintani zeta functions. So here's the data to which we associate one of these Shintani zeta functions. We'll let A be a D by N matrix with complex entries such that the real part of the ijth entry, I'm going to write the column in a superscript for reasons because it'll be useful later, so just forgive me. And I want the real part of all the entries to be strictly positive. This is essential for every I and j, and we'll take x to be a vector in Rd consisting of non-negative entries with the proviso that I'm not taking the 0 vector. And I can define this Shintani zeta function using a Dirichlet series. So the Shintani zeta function associated to these data is going to be the sum, where a multi-index k varies over tuples of d tuples of non-negative integers, and then I'm taking the norm of the following column vector a times x plus k. So x and k I'm viewing as column vectors, as d-element column vectors, and by the norm of a column vector, C1, Cn, I mean just the product of the elements, and this has got to be off the page. Almost. Minus s, thank you. That's right. Oh, n by d, I'm sorry. Okay, and this norm notation is suggestive because if we look at the n tuple of all the images under all the embeddings of an element of a degree n field, then the norm is exactly just the product of all of these. So in the situation where all this data comes from a number field, then this means what it should mean. And I should tell you about the convergence of this Dirichlet series. It's not hard to show that this converges absolutely and uniformly on compact subsets of the right half plane, real part of S bigger than d over n. Okay, and I should remark on the next page, perhaps. The n equals 1 case of this construction is just the Hurwitz zeta functions, more or less. So in proving analytic continuation and of Shintani zeta functions, we recover well-known facts about Hurwitz zeta functions. Okay, so it's a formal definition of a Dirichlet series. What does this have to do with partial zeta functions and number fields? So let me try to make that connection. I'll indicate the proof. Well, let me state Shintani's one of Shintani's main results on these is that these functions, zeta a x s, they admit meromorphic continuation. To the complex plane, and I'll indicate the proof of this later. After I convince you that these are relevant to the main topic of our discussion, so first I'd like to discuss the connection with partial zetas. And I'd like to make this connection in the case that's easiest to draw, the case of real quadratic fields. And hopefully it'll be fairly evident from there what the connection is for arbitrary number fields. So let's suppose that f over q now is a real quadratic field. And with embeddings, x mapping to xi. So I'll just denote the embeddings by subscripts. And let's take an ideal little f of the ring of integers of f, and let's, just for my convenience, let's choose this such that E of f, the totally positive units congruent to 1 mod f, is cyclic. So there are no roots of unity congruent to 1 mod f. And let me fix a generator for that group epsilon such that epsilon is between 0 and epsilon. Well, its image under the first embedding is a real number between 0 and 1. If it isn't, take its inverse. And we'll look at the array class field associated to this modulus f, and that's going to be the k that comes into the partial zeta functions. And let me choose an ideal of OF with a prime to everything in S. I'll take the S to be the minimal one, the set consisting of all prime divisors of f together with the infinite places. And I also would like to insist that A be relatively prime to F. Okay, so this is all the data that allows us to consider partial zeta functions, which I'll remind you the definition of. In terms of Dirichlet series, the partial zeta function relative to the extension k over f and the set of places S of the Frobenius automorphism of A evaluated at S is going to be the sum where B is an integral ideal of OF, which is prime to S, of the norm of B to the minus S. And we can write this somewhat differently. If we'd like to sum over elements instead of ideals to allow us to perhaps be a little bit more close to Riemann and his proofs of analytic continuation, what we can do is we can use this distinguished ideal A to generate systems of representatives for the ideal class for the ideals B. Yes, I want sigma B to give me the same element of the class group, ray class group as A, modulo F. Thank you. And so what I can do is I can write this as the sum over elements now, Z in 1 plus A inverse F, totally positive elements of that set, modulo E of F of the norm of Z to the minus F's. So I claim this is the same sum, and the reason is, well, the reason is a nice exercise to work out, that if you look at the map from 1 plus A inverse F, non-negative elements modulo E of F, and you map this to the set of B and OF, such that B is prime to S, and B gives you the same element in the ray class group modulo F as A, and you map an element X here to just X times A, then this is actually a bijection. All right, so these really do give you the same sum. And so this factor of n norm of A to the minus S is just to account for the fact that we're making a choice here, and we have to cancel it out somehow. So this is part 1 of this exercise, the part that proves this equality. And I'm going to add a part 2. And part 2 of the exercise is that if we look at the totally positive elements of F, then this can be decomposed into translates under totally positive units congruent to 1 mod F of a certain Shintani cone, which I'll denote C1 epsilon, closed on the left, open on the right for the moment, where C1 epsilon is defined to be the rational cone consisting of multiples of 1, which are rational and positive, plus q positive times, or greater than or equal to 0 times epsilon. All right, so in particular, 1 is in this set. Hence the closure on the left. And we can draw this set C of 1 epsilon. If I look at this to be the first embedding of F, and this axis to represent the second embedding of F, well, 1 maps to the point 1, 1, and I assume that my first embedding sends epsilon to a real number between 0 and 1, so epsilon bar, or epsilon 1, epsilon 2, I should say, lies somewhere there. And this cone is, in this C1 epsilon is simply this cone. And by the way I've defined it, I'm including this bottom bit. Okay, and by this part 2 of the exercise, what we have is that 1 plus A inverse F intersect C of 1 epsilon, intersect this cone, this gives us a set of representatives for the cosets of generators of the ideals that we had in the previous expression for the partial zeta function. So if we look at the map from here into 1 plus A inverse F positive mod E of F, just induced by the inclusion map of this into this, I guess if I'm going to do that I should say it's positive, although it's sort of redundant because C is in the positive quadrant, then this is an isomorphism because this is a disjoint union. And what we get from this is that zeta K over F S of sigma AS is going to be norm of A to the minus S times the sum, where Z is in 1 plus A inverse F, intersected this cone, and I evaluate the norm of Z and raise it to the minus S. And now, here I'm summing over honest elements. In the previous one, I was summing over elements modulo units, modulo things of norm 1, but here there are no more choices involved. I've already made my choice by fixing this cone. And that's convenient for the analytic continuation purposes. Now, the fact that the boundary conditions are asymmetric now becomes annoying. So there's a simple fix. I'll just write C of 1 epsilon as C of 1 disjoint union C now open at 1 epsilon. Or C of 1 is just the cone spanned by 1, so just the shaded line, not including 0, and C of 1 epsilon is now the interior of the cone. And what I get is a corresponding decomposition of the partial zeta function. I'll get norm of A to the minus S times two sums, the sum now over 1 plus A inverse F intersects C of 1 plus a sum over 1 plus A inverse F intersects C of 1 epsilon. All right, and these two are both sums involving lattice points lying in certain simplicial cones, so they're the same sorts of creatures and we can treat them simultaneously and uniformly. Okay. Now, I still haven't made the relation explicitly with Shintani zeta functions, so let me draw another picture to show you how that comes about. So what I've reduced, the way I've expressed my partial zeta function now is a sum over certain points in a lattice translate over norms of points in a lattice translate which happen to also lie in my cone generated by 1 and epsilon. And the points in this, the lattice points in this cone have a finite generation property, which is a standard geometric fact. Because these endpoints happen to lie in our lattice translate, because epsilon is congruent to 1 mod f, you can generate any point in the cone by adding an integer linear combination of 1 and epsilon to some point in this fundamental parallelogram. So let me call this fundamental parallelogram P. And what one can show is that 1 plus A inverse F intersect this cone, C of 1 epsilon, is the disjoint union over points Z in 1 plus A inverse F intersected with this fundamental parallelogram of this cone of the sets z plus non-negative integer multiples of 1 plus non-negative integer multiples of epsilon. And note that this, I have a discrete subset of a bounded set, so this is a finite disjoint union. And breaking up my zeta function accordingly, what I get is that the sum over 1 plus A inverse F intersect C of 1 epsilon of n of z to the minus s. This is going to be the sum over, again, z in this set, z in 1 plus A inverse F, now intersect C of 1 epsilon. But now I'm subject to the assumption that z can be written as x1 plus x2 epsilon, where xi is a rational number between 0 and 1. These subscripts on the sums are getting large. And then I can take the sum over double indices k of non-negative integers of now the norm of x1 plus k1 plus x2 plus k2 times epsilon. Right, and this is beginning to look a little bit more like these Shintani zeta functions, and in fact it is. Minus s, yeah. What? No, this is the, yeah. So what this is equal to is the sum over these same z's of the sum over the same k's of now the norm of the following vector 1 epsilon 1 1 epsilon 2 times the column vector x1 plus k1 x2 plus k2. And I'll remember the minus s this time. Right, and this really is a Shintani zeta function now. And note that because epsilon's a totally positive unit, this matrix has positive entries, which is essential for Shintani's method. Okay. Now, the picture is simple to draw for real quadratic fields, and correspondingly the expression of partial zeta functions in terms of Shintani zeta functions is straightforward for totally real fields. By the way, I'm using that I'm leaving that one-dimensional cone to you guys. You use the same technique to write it in terms of Hurwitz zeta functions, Shintani zeta functions, sorry. But in fact, this is fairly general due to the following theorem of Shintani from the same paper. If F is any totally real field, and all the symbols are as above, then there's a finite set of cones in the positive piece of F, such that this positive piece is the disjoint union, as n varies over z, of the disjoint union as we vary over the cones of epsilon to the n times c. So we can find a finite collection of cones that, under the action of the totally positive units congruent to 1 mod f, tile the totally positive elements of f. And then, using all of these cones instead of these two cones that I happen to be able to draw nicely here, you run the same argument, and you can decompose the zeta function of a totally real field into however many cones you have, and of some number of Shintani zeta functions depending on the number of cones you have and the number of lattice points in the fundamental parallelograms of each of those cones. Sorry, I should say epsilon, maybe I should say epsilon varies over E of F. So over the whole group of units congruent to 1 mod F. Sorry about that. And now I don't need an exponent here. So what we've shown, I guess I should write this out explicitly, it's the main point that norm of a to the s times zeta k over f s of Frobenius of a s, this is a sum of Shintani zeta functions, a finite sum. Okay. So let me move on to part 3 of the talk, which is talking about the analytic continuation of Shintani zeta functions. And an interesting feature that comes out of this analytic continuation method is a decomposition of the Shintani zeta functions indexed by embeddings of our totally real base field into the real numbers. So although this starts off as an analytic trick for meromorphic continuation of these zeta functions, it actually has arithmetic content in the sense that it allows us to write down fairly precise formulas for Stark units. So at least at the start, the analytic continuation process for Shintani zeta functions resembles Riemann's second proof of the analytic continuation of the Riemann zeta function. It starts off with Euler's integral, which is that the integral from 0 to infinity of e to the minus nt, t to the s, dt over t. If you do a change of variable, what you'll get is you'll get the gamma function coming out. Well, this is a gamma integral essentially, but the change of variable will cause an n to the minus s to come out of this. And if you sum now over n, you'll get the gamma of s times the Riemann zeta function on the right-hand side, and you'll get the integral of some geometric series inside that integral. And that's the start of Riemann's second proof of the analytic continuation of zeta. So let's look at the n-dimensional version. In other words, the version for Shintani zeta functions. And what you get is gamma of s to the n times zeta of axs, where the A is an n by d matrix and x is a d element column vector as before. This will be the integral over n copies of the, or did my battery die? Okay, no, I'm back. But my battery indicator's a red light. Of e to the minus tax times the sum over d tuples of non-negative integers of e to the minus tak t to the s dt over t, where, should explain some of this short. I flipped it back on and off, but okay, we're back in business. All right, so I should explain some of the shorthand in this in the integrand here. So t, I'll view as a row vector. So the multiplication in the exponent there makes sense and gives me a number. And t to the s dt over t means what you think it means, just t1 to the s times tn to the s times dt1 dtn all over t1 times Tn. Okay, so that's what you get by applying the exact same Eulerian integral, this time n times. Once with respect to each variable ti. And, well, in the original version, for the Riemann zeta function, you end up with a geometric series. Here, what you actually end up with is a product of d geometric series. Which, when you sum them, gives you the following. So we'll have the integral from 0 to infinity, nth power of that interval, of a sum I'll call g of t, the sum of that creature, times t to the s dt over t, where g of t is the following expression: the product as j runs from 1 to d of e to the t a j 1 minus xj, so a superscript j is the jth column of the matrix A, all divided by e to the t a j minus 1. Okay, so that's what I get by summing the geometric series. And now if I want to continue mimicking Riemann, what I'll do is try to integrate this over what's called a Hankel contour. So the way Riemann proved the meromorphic continuation and other properties of the Riemann zeta function is he expressed this integral as a contour integral which converges essentially everywhere. So this integral converges exactly where the sum we got it from converges, but we can write it a little differently. We can write it in terms of a path integral along this contour. So here, what we have is our variable t is going to travel from infinity along the real axis to epsilon on the real axis, then circle the origin counterclockwise, and then travel back along the real axis. So I have to tell you what the integrand means on this contour, which means I need to tell you how to define the logarithm. So the way we're going to define the logarithm is that on the inbound part of this contour, we'll consider the argument of t to be 0, and on the outbound leg, we'll consider the argument of t to be 2 pi. I need this for the continuity of the integral, and if you're a little uncomfortable with me defining the same point to have two different arguments, you can integrate on the universal cover of the punctured complex plane, where where you don't need to choose a branch of the logarithm. It amounts to the same thing. But where Riemann integrated over just the simple Hankel contour, we would need to integrate over something like the nth power of the Hankel contour. So let's see where that might get us. Let me set I epsilon equal to the integral over the Hankel contour to the power n of what I had before. The product as j runs from 1 to d of e to the t a j 1 minus xj divided by e to the t a j minus 1, t to the s dt over t. All right, and now the cases n equals 1 and n greater than 1 diverge. Let's look at the case n equals 1 for a moment, in which case we know everything is well. In this case, the denominator, this is the case of Hurwitz zeta functions, by the way. The denominator in that integrand, or in the rational part of that integrand, is e to the t a j minus 1. Now t is only a single variable now, not a tuple of variables. So this has an isolated 0 at t equals 0. But so there's no problem on the contour. But in the case where n is bigger than 1, the denominator, let me write it out longhand, is e to the t1 a1j plus t2 a2j plus dot 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 plus tn ajn minus 1. And now this can be 0. This is 0 along the whole kernel of the linear transformation dot producting with the jth column of A. Right? So this is 0 along a hyperplane. Through the origin. All right, and a product of n copies of the Hankel contour. Well, a piece of this is the polydisk of radius epsilon. But any polydisk of radius epsilon around the origin will intersect this hyperplane along which the integrand is singular. So the integrand is not holomorphic on c of epsilon of infinity epsilon to the n for any epsilon. Which means that, well, the Riemann's method seems to have just broken down. Shintani's insight was how to fix this problem. And his fix was to subdivide to go back a step and subdivide the region we're integrating over, namely the product of n copies of the open interval from 0 to infinity. He'll write 0 infinity as the union, disjoint, of n sets, I'll call di, where di is defined to be the set of all tuples t, such that ti is the biggest element in the tuple. Thank you. All right, and in every tuple, something's the biggest, so this covers my product of those n intervals. And on each di, we'll do a different change of variable. On di, I'll change t to u times y1, yi minus 1, 1, yi plus 1, yn. All right, so I'm setting, in other words, I'm setting ti to be u, and yi to be t, and yr to be t over u, or tr over u, for r not equal to I. And note that this is less than 1 because u is ti, which is the biggest among all of those components. All right, so note that yr belongs to the interval 0, 1 for all r not equal to I. Okay, so our integral over 0 infinity to the, too low? Next page. So our integral over 0 infinity to the n turns into an integral over 0 infinity of the integral over 0, 1 to the n minus 1. So that's the first stage of his decomposition. And now, instead of looking at the nth power of the Hankel contour, what I'd like to do instead is consider, well, I want to integrate the u variable over the Hankel contour, but all the y's, well, the y's are all at most 1, so instead of starting my Hankel contour at infinity, I'll start it at 1. Right. So this is C1 epsilon, and so now my integrand is, so this will be, here I'll have a u to the s du over u, and here I'll have an e to product, as j runs from 1 to d, of e to the u y aj times 1 minus xj, divided by 1 by, e to the u y a j minus 1, and then I'll get a product over r not equal to I of yr to the s dyr over yr. You do the change of variable and you'll see this is what you get. And this is encouraging, because if I write out the denominator here in longhand, what this is what do I get? I'll get e to the u times y1 aj1 plus dot dot dot, and then in the ith, I have a coefficient of 1. And let's see what happens if we take our point uy to be on the Hankel contour. So let's take u to be on c infinity epsilon, which means that the modulus of u is epsilon, or is at least epsilon. So this u is not 0, and well, we want the y, we want the y's. We want to consider the part of the contour where we circle the origin. So let's consider y's of modulus 1, so things on the polydisk of radius epsilon. And if we take, because all of our entries of our matrix A are assumed to be positive, if y is small enough, then this will be essentially just AI1. All right, which means that it's not going to vanish for epsilon small enough. So we see that the integral, or this contour integral, is holomorphic on the contour for epsilon small enough. Okay, so summarizing, if I define, so this isn't exactly the same as this integral, right? You have to fiddle around with it a bit. You're integrating over the interval from 0 to infinity twice, one in each direction, but with different arguments, so there's a discrepancy there. If you define zi of axs to be 1 over gamma of s to the n times e to the 2 pi I n s minus 1 times e to the 2 pi I s minus 1 to the n minus 1, times j epsilon, then what you get is that zeta of axs is the sum, as I goes from 1 to n, of zi of axs. And now that we have a contour integral representation for each of these zi's, they can be analytically continued using standard methods, and therefore their sum, the Shintani zeta function, can as well. So as we've seen it so far, this trick of Shintani to decompose the domain of our Euler integral into n subsets, well, it has a wonderful analytic consequence that allows for meromorphic continuation of these very general kinds of zeta functions. But what we'll discuss next time is the arithmetic application of this decomposition to things like zeta values and Stark units. So I'll leave it there for now.